morning everybody. So, we are back again with fluorescence spectroscopy. So, in last lecture we tried to understand what is green fluorescent protein and why this is important, because biological system having such fluorescence property, such a biocompatible system which will enable us to study cellular processes. Okay. So, these are very important, and nowadays this chemistry, especially spectroscopy, has entered into many domains of fundamental science or natural science, because spectroscopy is the tool by which you can study environment, okay, you can study some interaction, okay, you can study some specific processes, you can also focus onto maybe some part of a cell by means of microscope. So that is why fluorescence spectroscopy has been and is continuing to be an important partner in basic science, basic of course experimental science, because experiment is gives you the certainty thing. It is the mother of certainty. Okay, so that is, if you make a model and you say that this may be happening, so it's of course, and I mean this modeling is important, but as long as this is not verified experimentally, then anybody can argue that maybe another parallel model of a little different modification can also explain the observed phenomena. So that is why experimental verification of something is essential. Apart from the modeling and theoretical development, this is also important, and experimental spectroscopy, especially fluorescence spectroscopy, is continuing to be an important ingredient in the experimental science. Now, so we talked about this GFP fluorescence, where this GFP, this green fluorescent protein, it has it can be put inside, it can be put inside the cell, and then you can study things. So these are the positive points, and nowadays different variants of GFP are developed. So this all the things we talked about in the last lecture. Now today we are going to give you some examples where fluorescence spectroscopy has been applied, or fluorescence and maybe UV visible absorbance spectroscopy has been applied in understanding important phenomena in protein system, in biochemical system. Now, in this regard, we talk about this ligand binding processes. Now, what is a ligand? Now, all of you can remember this in Werner's coordination theory. So, like you think of ethylene diamine tetraacetic acid. Okay. So, this ethylene diamine tetraacetic acid, it acts, it sequesters some metal ion, producing a complex compound. Okay. So, and this is I mean it is coordinating with the metal. So, these are the ligand centers, okay, different ligands which is coordinating the central metal and forming a complex. So, in that respect it is called the ligand. So, something what is binding with the system of our interest, okay. So, may be called as ligand, and ligands can be exogenous ligand, that means the ligand which is coming out, I mean which is coming from outside. So, you are adding something into the system, and then it does something. So, it is exogenous, that is which is gained from outside. Maybe in some cases ligand can be endogenous as well, because maybe if you have a complex structure and because of something what is happening, that maybe you have got a complex structure, that maybe this part is coming out over here and doing this binding, okay, this way, okay, and binding with this, okay. So, like this. So, it is coming from within the molecule. So, it can be an endogenous ligand, okay. So, this ligand binding is an important thing, and in most of the cases, like if you think of this hemoglobin or maybe myoglobin, so it is a transport protein, okay. This hemoglobin, it transports oxygen from one part of the other, okay. So, this what is happening, that our oxygen is coming from outside, it binds with the iron center, okay, and then wherever it is required to be released, it is released, and maybe depending on the physiological condition, binding becomes weak out there, and therefore it releases oxygen, and therefore oxygen does its important functions, okay. In that respect, ligand binding is important, okay. Maybe you have some suppose you have some drug, okay, which has to be transported to the target place. So, what is happening? Maybe there must be some vehicle, or there must be some machinery which will take up your drug, bind with the drug maybe for the time being, and then it will be transported to another place where it needs to be released. So, it will be released and it will do its function out there, okay. And then after its function, then maybe biologically it will be degraded or something else, okay. So, this drug will be ultimately metabolized, you will be getting the metabolized drug metabolized product. So, this particular process, I mean this ligand binding is important, and understanding of this ligand binding process is even more interesting and important from the point of view of the fact that that what is exactly happening. Maybe the examples which are going which I am going to describe or give to you is all are in vitro studies, I mean outside the cell, maybe in laboratory condition these are studies, this is not in vivo, but using physical chemistry principles and maybe principles of spectroscopy, we would try to understand the process, and process means what is exactly happening out there, okay. So, in this regard, first of all we will take the example of this food dye. Now, food is an important stuff which all of us know that we take every day, and food dyes are this food coloring stuff. Now, the point is why I have taken, you could have taken other examples in dealing with this particular thing, that is application of fluorescence spectroscopy in understanding protein ligand interaction. You will be getting plenty of examples in literature, like binding of something with X protein, and then this binding will give you, I mean you can follow it maybe a non-spectroscopic method using some other technique, maybe equilibrium dialysis is also a technique by which you can follow this binding process, or maybe you can follow it spectroscopically. So, you can study study many things. So, many things and a lot many examples can be found in literature. Okay. So, here we have taken some of these things and we have taken the example of this food dye, of which one is of course synthetic food colorants. Okay. And we want to discuss, I mean, this interaction with protein. Now, food dye is carmosine is an important food dye. I mean, important in the sense that it is used in many places, that is used for producing colored food, colored cosmetics and colored medicine. Maybe if you look into different allopathic medicines, you will be finding that some of them are colored. So, actually the color is not due to the color of the drug, but it is some of the colors are some colors are put out there because of it may be because of because I mean in order to make it attractive, or maybe just for some, maybe it is acting as indicator. Okay. Maybe after it is metabolized, maybe some color change is happening. So, just to have some indication of whether this is when the color is fade, means maybe it is totally metabolized, or else there may be some clinical reason for putting the color, or maybe just to make it attractive. In the same way, these food colorants are, the synthetic food colorants are also coloring substances. These are generally water soluble, and these are synthetic azo colorants, and of which carmosine is one synthetic colorant, and this synthetic colorant is having like red type, around 515 nanometer its absorption maxima. So, it is towards red. So, what is happening that this carmosine has been used for maybe this toothpaste coloring, maybe coloring some food material. Okay. These are generally these are, I mean, these are water soluble synthetic azo dyes containing sulfonate group. So, therefore, they are water soluble, and they are stable in wide pH range, and they are also thermostable. I mean, temperature stability is also high, because maybe in some of the foods when it is processed, maybe heat treatment is there. So, if the color is lost due to heat treatment, then putting of color, I am putting that color, it may not be of any use. Okay. So, that is why after heat treatment, if it is lost, so that is why it has to have this temperature stability. Now, here we are just I mean, we are presenting its interaction. I mean, some of the glimpses of this study, interaction with serum protein. Now, the point is, you can ask one question: why serum protein is important? There may be many other proteins. Now, the point is, serum protein is highly abundant. I mean, you can get it from the market. Okay. And its structure is, I mean, it is widely studied. So, details about its structure, etc., structure, and what are the important parts in that protein, okay, that is also known. Now, so therefore, serum albumin is the most abundant protein constituent, is the most abundant protein constituent of blood plasma. So, in blood plasma, you will be finding serum proteins. So, that is why it is, and it is a transport, it is a transport protein. Okay. So, transport of different constituents, and the important point is that it has got some portions, I mean some parts in the protein called maybe pocket or maybe some domain. Okay. There are many domains in that protein, and as a result of presence of domains of different kind, it is found to bind various substances starting from metal to drug, etc., etc. That is why this is one of the important candidates for the study of various ligand binding phenomenon in general, and it has a key role in maintaining blood pH. It facilitates the deposition and transportation of various endogenous and exogenous molecules. Those are called ligands, such as dyes, drugs, fatty acids, steroids, metals, and so on. So, in that respect, serum albumin is an important thing to explore. Now, what is the importance of protein ligand interaction and for which we are interested now, because in this case protein ligand interaction will be followed spectroscopically using fluorescence spectroscopy. Now, why do we want to study protein ligand interaction, especially in reference to serum albumin? Maybe you can study other proteins as well, or if you look into the internet, then maybe you will be finding plenty of examples involving other proteins as well. Okay, involving other proteins as well. So, now serum proteins are studied over here because serum proteins are well studied proteins and they have several binding pockets specific to different ligands. What are the binding pockets? Because as I told you, proteins are of a peculiar structure. It is a three-dimensional folded structure, and whenever it gets folded after this post translational modification. So, what is happening that after this post translational modification, maybe some of these, you will be finding maybe there are grooves, or maybe there are channels, and maybe some holes are there within this three-dimensional structure. Okay, those are called pockets, or maybe some clips. Okay. So, and the serum proteins have several binding pockets specific to different ligands. Okay. Negative sulfonate and also this negatives, means here carmozine and other food dyes, water soluble food dyes, which we are trying to focus on. These are having negative sulfonate groups of azo dye, which may interact with basic side chain of amino acid residues of protein through electrostatic forces. So, basically in this particular study, electrostatic force of interaction will be followed, maybe if there is some contribution of that. Now, the point is, where does this electrostatic force come? Now, point is, whenever there is interaction, now interaction means, think about say benzoic acid dimer formation. Okay. So, benzoic acid dimer formation occurs via this hydrogen bonded interaction. So, interactions can be of various kind. One is electrostatic in nature, which is as a result of electrostatic interaction. Maybe you have got a plus charge, you have got a minus charge. So, they ought to interact, ought to attract each other, or maybe if it is a minus charge, it is a minus charge, they ought to repel each other. So, this is as a result of electrostatic interaction, and this is your this interaction is guided by this Coulomb interaction model. Okay. So, electrostatic interaction, maybe non-electrostatic interaction like hydrogen bonding interaction, then maybe van der Waals interaction, so on. So, therefore, whenever there is ligand binding interaction, then which particular factor among this electrostatic or non-electrostatic is important, or whether one particular force is present there and the other force is absent there. So, that is also important. So, that can be diagnosed with the help of fluorescence spectroscopy. Okay. And we are curious to know what happens with an azodie having 2,3 sulfonate groups with anticipation that there will be a pronounced electrostatic interaction. So, basically it is a curious thing. I mean, it is a matter of curiosity that that if there is a sulfonate group, then there is a possibility of some electrostatic interaction. Now, this is the structure of, I mean, crystal structure of taken from RCSB PDB with ID 1A06, which is called the human serum albumin. Okay. Now, human serum albumin is a big protein. Now, it has got like 1B subdomain, then 3A, then 3B, this is 2B, 2A, 1A. So, various subdomains are there, and there are two sites, important site. One is site 1 subdomain 2A, another site 2 subdomain 3A. So, these are the various parts of the protein which may interact with your ligand, I mean exogenous ligand. So, in this case different experimental conditions are used, because I mean it has been, in this particular case, it has been attempted to explore this effect of charge or the effect of other things. So, therefore, experimental pH has been varied between this 4.8 to 7.4, and variation of ionic strength has been done at some fixed pH, that is pH is fixed, ionic strength is changed. Because whenever you do all these studies, you need to make the solution, that is protein solution, at some buffer, because you have to keep the pH of the solution fixed. Why it is important to keep the pH of the solution fixed? Because suppose that you add something from outside, and something means some ligand from outside, and the thing is such that as a result of addition, you do not use a buffered solution, suppose, and you as soon as you are adding this substance from outside, although maybe in a minute quantity, it may so happen that it tends to alter the pH of the solution, and if the process of interaction is very much dependent on the pH of the medium, then maybe that may affect this binding interaction. So, therefore, it is necessary that you buffer this solution, so that little alterations of pH is taken care of. Now, typically absorbance spectra of carmosine, the following things have been done to know about what is happening. Now, you see that first look into the fluorescence emission spectra. Okay, you see that as you increase the concentration, as you increase the concentration of your ligand, that is carmosine over here, you see that its intensity is reducing. This is your HSA emission without any quencher, because we will study this interaction taking help of the fluorescence quenching methodology. Okay. So, we will follow this interaction. I mean, this interaction has been, we can follow such interaction. So, interaction has been followed, okay, has been followed by fluorescence quenching process. Okay. So, fluorescence quenching process. So, quencher is carmosine. Quencher is carmosine. So, as you increase quencher concentration may be, sorry, this should be like this, it is doing like this. So, fluorescence is quenched, and this is perhaps you remember that we are using, we are making use of this intrinsic protein fluorescence over here. Okay. So, intrinsic tryptophan fluorescence of this serum protein. Tryptophan fluorescence, because this carmosine is not fluorescent. So, therefore, there will be no interference with respect to fluorescence due to carmosine. So, this is your fluorescence intensity, fluorescence, and this is your lambda. Okay. You see that this tryptophan emission is around 350, okay, around 350. Recall this position of this tryptophan fluorescence. So, it looks like that this tryptophan is exposed to solvent, that is why it is red shifted. It is I mean exposed, and it is in polar environment. Okay. So, if we increase carmosine concentration, it is reducing. So, you see that this is the Stern-Volmer plot, quenching plot, F0 by F as a function of concentration. You see that for HSA, you see at different pH, nothing is happening. Now, now the question is it something important? Is it something important? Is it an important observation that nothing is happening as a function of pH of the medium? Okay. And another important point is, you see that there is a little you see that there is a positive deviation of Stern-Volmer plot, and you see that it is insensitive to pH. Now, what is exactly happening? Now, the thing is that whenever this carmosine is added to this protein solution, you see that there is a shift in means when you increase the HSA concentration, you see that there is a shift in absorption maxima about 6 nanometer. Okay. And this is because of the fact that there is a ground state interaction. Okay. Ground state interaction, and therefore, ground state interaction and no change, which is responsible for the this emission quenching. Okay. And there is a little shifting of emission towards the shorter wavelength, which indicates that alteration of the microenvironment of this chromophore. Okay. Chromophore is your tryptophan as a result of this addition of carmosine. Now, this protein ligand interaction has been followed by means of some interaction model, which is called the Scatcherd equation, and this Scatcherd equation is as follows. So, which talks about the saturation model, fractional saturation. This is using some absorbance data and fluorescence data. So, it says that it is specific in nature. So, some specific binding is happening. Okay. So, this is a fractional saturation plot. Fractional saturation plot means you have got this maybe for some protein. Okay. So, you have got this pocket. Okay. So, saturation means it is fully saturated. Means 100 protein molecules. Okay. And when you increase this carmosine concentration, So, initially it is maybe 50% saturated and then maybe 100% saturated. So, after 100% saturation, what is happening, there should not be any change in the property which you are looking for. So, up to this it is fully saturated, okay, some property as a function of concentration. Okay. So, this saturation says that this interaction is specific in nature. Saturation says that is the interaction specific. So, this interaction is specific in nature. Okay. So, Scatchard equation in modified form it is done, and also as I told you that it is a multiple, I mean whenever we use this type, I mean whenever this type of studies are done, then all the possibilities are explored to diagnose what is exactly happening. It is not that just fluorescence is only simple fluorescence has been followed. Okay. Now, in this case this Scatchard equation, I mean an equation which talks about, I mean it is derived from a model. So, Scatchard equation has been used up to probe this interaction, and binding constant for the process as a function of temperature, all these things are done, and it is found it is reported that binding constant decreases with increase of temperature. So, binding interaction has been found to be thermodynamically spontaneous and high positive entropy and low negative entropy, positive entropy and low negative enthalpy changes are found. Now, interesting thing for this particular study is that you see that when you change salt concentration, I mean salt concentration means added salt from outside, you have added salt from outside. You see that for HSA and for BSA, these are the two parallel proteins are used, one is bovine serum albumin, another is human serum albumin. You see that it is decreasing 10 to the power 6 to it is decreasing. So, this interaction becomes weak as you increase the salt. So, what does it indicate? Okay, it indicates that salt affects this interaction. So, interaction is affected by salt means it is electrostatic in nature. Now, so electrostatic in nature means you have got this electrostatic interaction, and so plus and minus. So, salt interferes into it and reduces this interaction, because salt interacts with this one and salt also interacts with this one. So, that this interaction between these two original entities are reduced. So, therefore, it is electrostatic in nature, and thermodynamic studies, because you can study thermodynamics with the help of this this binding model. I mean you study binding constant, you determine binding constant maybe with the help of this equation, and then at different temperatures you do that binding. So, from this binding studies you can, I mean with the help of Van 't Hoff's plot you can get this enthalpy and entropy. So, enthalpy entropy gives you an idea of whether the process is electrostatic or non-electrostatic interaction. So, some numbers, I mean something, if you I mean depending on the value of this entropy and enthalpy contribution, it can be diagnosed that whether it is electrostatic or non-electrostatic in nature. And fluorescence decay, fluorescence studies are also done, but most interesting and important study in this particular case is that this effect of salt we have has been found, and so the point is, and also this for BSA another important information is that this, although this study has been done with carmozine HSA and carmozine BSA cases, but in case of carmozine, then point is carmozine is binding. Now, if you say that carmozine is binding with the protein, so maybe for a well studied and well information, I mean the protein information about the protein is known to us. I mean it is a very well studied protein, this BSA and HSA. So, now if I say, or someone says that the study says that it is binding and binding constant is this, and maybe thermodynamical data also says that maybe this binding has got this type of nature, okay, and maybe binding is also electrostatic in nature. So, one point which is still lacking over here is that whether you can specifically see that this ligand has gone to this pocket, this particular area, this particular region of the protein. So, then how to diagnose? So, important thing is that in this type of studies, what is done that since this protein is well studied, you have got some set of different molecules which are known to bind some specific positions of the specific pockets of this protein. Now, what you do? So, how to know that where this your molecule is binding? How to do that? It is very simple, that you pick up one of these known molecules which are called site markers. Site markers means that if you add that site marker molecule, then it will specifically bind to maybe this specific region of the protein. Okay. Now, what you do in presence of one site marker, you do or you study the binding of your ligand. I mean, first you saturate your protein with the site marker, then the saturated protein has been subjected to the fluorescence studies, okay, involving your ligand, and see whether the binding whether you get any binding or not, or binding of your ligand is weak or not. Okay, that gives you an idea that maybe your ligand is competing with the site marker. So, if it is competing with the site marker, means that they are looking for the same site, otherwise there should not have been any competition. So, if you study this competitive binding in presence of those site markers, you should be able to know where this ligand is binding. Okay. So, in case of HSA, warfarin is one site marker and maybe hemine is another site marker. It may be ibuprofen can be another site marker, like this for this serum proteins. These most studied or the common site markers are warfarin. Warfarin is an anticoagulant drug, then hemine. This is iron porphyrin system, and ibuprofen. Ibuprofen is basically another painkiller. So, these are the three things. So, in presence of this, if you study, then you should be able to know where it is binding. Okay. So, subdomain 2A is for warfarin, subdomain 3. Let us go to the earlier slide. Subdomain 3A and subdomain 1B. These are the three regions of interest. So, it is found, it is reported that it is found that this binds, in case of HSA, only competition has been found with warfarin, but in case of BSA, it is another protein. This is having, it is homologous to HSA. So, it has got sequence homology with HSA, means they have matching sequence up to some percentage. Okay. So, BSA HSA are very they are homologous proteins. So, it has been found that for BSA, this particular particular ligand carmoisin, in case of BSA, both warfarin and hemine has been found to compete with carmoisin. What does that mean? That's a quite interesting result. What does that mean? So, it means that maybe suppose you have got, say, this is your protein, and say this is the site maybe for which is site for warfarin, and say maybe this site for hemine. Okay. And suppose if your drug is binding over here, then warfarin will compete with your drug, or if it is binding over here, it will compete over here. But suppose the drug is binding maybe in this way, then what will happen? Then warfarin will also have influence on this binding, and also this hemine will have influence on this binding. So you see that if this is happening, means it is binding in a region where, I mean, there is a common intersection region. So you see that site marker fluorescence studies can diagnose where this ligand is binding, okay, whether this ligand is binding a specific pocket or maybe in between that. So that is why this is just to give you an idea that how fluorescence spectroscopy can be successfully utilized to understand the nature of ligand binding, be it electrostatic, be it non-electrostatic, and also the very specific region where it is binding, very specific region where it is binding. So this is important, and also in some cases fluorescence decay, I mean tryptophan fluorescence you can monitor, and tryptophan fluorescence decay can give you information about what is exactly happening. In most of the cases fluorescence decay, although I am not going into the details of what has what is there in fluorescence decay experiment, but grossly what I want to say, that suppose, I mean at the very start of this today's, I mean start of this particular topic of discussion, that it is a ground state interaction between this protein and carmosine. So if it is a ground state interaction, means excited state interaction is not there. So that means fluorescence of tryptophan is not, should not be coincident. That is why you see that there is not much change in fluorescence profile with increase of concentration of tryptophan. That means that tryptophan is rather at a distant place compared to your ligand, where the ligand is binding, or maybe tryptophan is somewhat somewhat protected. Otherwise there should have been a lot of change, but change is not that much. I mean it is not a huge change, but maybe it is affected to a little extent. But if it is a direct excited state interaction, maybe you could have expected more change. So fluorescence decay gives you a lot of information about it. So in turn what it can be stated that it is specific interaction we can follow, whether interaction is electrostatic or non-electrostatic, that you can also diagnose. Okay. So and what is the use of this ionic strength effect? So ionic strength effect you can use to to monitor, I mean to control binding of such thing. Okay. So I mean that you can get, if it is electrostatic interaction, then maybe salts can have profound effect on binding. So this is important. Okay. And so and also how these ligands or these exogenous ligands can be toxicologically toxicological profile can be followed. I mean not directly by means of this fluorescence spectroscopy, but toxicological studies can also be complemented with this fluorescence measurement. And other things, I mean contamination of food stuff with this food dye is likely to be affected, I mean likely to affect the absorption of drugs in blood plasma and may result impaired activity. So this study may have given us given people to understand that these food dye stuffs are sometimes they are not they are not good, in the sense that azodyes are not, I mean can be toxicologically it is toxic substance. So that is why and also importantly it is pH insensitive means another important point. So, these details of this interaction, I mean what I mean to say that details of interaction of an exogenous ligand with protein can be very efficiently followed. So, this is the success of fluorescence spectroscopy. So, in this type of particular studies, I mean particular study is a complete study where various aspects of fluorescence spectroscopy can be used to identify the nature of interaction, strength of interaction, and the region where this interaction is principally and primarily located. Okay, so next another example is whether this suppose you start with some prototropic ligand, that is ligand whose activity or a drug whose activity is dependent on this prototropic equilibrium. Prototropic equilibrium means you have got a say drug with proton, and it is doing like this D minus and H plus. So, it is conjugate base, okay, and this is your acid, and suppose that this is the active form, this is the inactive form maybe. Now, the point is whether such interaction, I mean such interaction with protein stuff, okay, and you can follow this fluorimetrically. So, you can follow spectroscopically. So, whether such interaction with protein will change this equilibrium. Maybe in aqueous system it has got certain pKa value. pKa value means this acid constant negative logarithm of Ka. Okay. So, that is a pKa. So, suppose pK in buffered solution is having some value, okay, but the moment it binds with a protein, what is going to happen? Whether this pK is going to be affected or not at all, it is affected. Okay. So, and also the point is, in this case you should keep it in mind that the interaction is guided, in some cases your ligand interaction with the protein is guided by electrostatic interaction. In some cases it is guided by non-electrostatic interaction. Now, the point is, where does this electrostatic interaction come? Means who is going to supply the complementary charge within the protein? As I mentioned in just a few minutes back, that maybe these side chains, I mean side groups, side chains of this amino acid residues, different amino acid residues have different type of side chains. One is it may be neutral type, it may be cationic type, it may be anionic type. And suppose that your drug which is suppose the conjugate base, this negative one, is interacting with a positive charge, that is positive side chain. What will happen? That it is going to stabilize. I mean, whenever it is binding, this -1 is binding with that. So it is going to stabilize this D minus. So, destabilize means D minus means it is going to affect this equilibrium, maybe in this side, this right hand side, or maybe in the left hand side, that is maybe in this H plus side, or maybe in this DH side. Okay. So, depending on this shifting of this equilibrium, your the pKa value can be modulated. Okay. So, and we are going to look into this particular aspect of study of this equilibrium. It is called the prototropic equilibrium. So, prototropic equilibrium means this shifting of proton from here to here. So, movement of proton from bound state to unbound state. So, it is called the prototropic equilibrium of some acidic gas. So, some typical example I am going to provide you, that will give you an idea that this binding and then binding, how this binding is going to affect the property of the drug or maybe the exogenous ligand, and how that can be followed fluorimetrically. So, our main concern is the application of fluorescence spectroscopy in various aspects. Okay. Especially in this particular part, we are focusing onto your this prototropic, I mean focusing onto this stuffs involving involving proteins. Okay. So, in that case, the point is the acidic guest in supramolecular and biosupramolecular nanocavities. Now, why this biosupramolecular? Because proteins have small cavities, and those cavities are almost they are nanometer sized. So, this in these nanometer sized cavities, the ligand is binding, and because of binding, maybe out of these two forms, maybe one form is preferentially bound to the cavity. Okay. And that leads to change in equilibrium position. Okay. So, negatively charged food dyes, still again it is a discussion with respect to food dyes that bind with positively charged side chain of amino acid residues by electrostatic complexation, like carmosine I just talked about, and maybe in subdomain 2A cavity. Okay. Subdomain 2A cavities. Now, like this, these are the typical, I mean food dyes that are generally employed for this type of studies. You see that all of them are sulfonated. Sulfonated means these are typical, these are mostly negatively charged. It is called cochineal red A, this is carmosine, this is tartrazine. So, this tartrazine is just faint yellow colored, you will be finding in many soft drinks. Okay. Now, the subdomain 2A, think about the subdomain 2A cavity, this one, and all these are binding to subdomain 2A cavity. Okay. Now, subdomain 2A cavity, it is binding, and it is also well demonstrated that the principal mode of interaction is electrostatic. It is electrostatic in nature. So, therefore, it may be thought that this some complementary charge is there. Some complementary charge is there within the pocket. Okay. And maybe this pocket is maybe that is acting as anion receptor, that is receptor of anion. So, this anion reception can be followed in principle by fluorescence spectroscopy. Okay. So, it is just to see whether fluorescence spectroscopy can be successfully employed to understand this prototropic behavior, of this acid, this gas. These are basically acidic, because you have OH, okay, acidic gas. Okay. And this is HSA structure. So, it gives you an idea that here is the pocket. Okay. So, now in this case, what is attempted over there is in this case two things are compared. Okay. One is warfarin. Okay. Warfarin means this as just I talked about this site marker. So, this one, and another is coumarin 343. This is another acid, but fluorescent acid. Okay. The thing is that using this two systems, one can just simply look into this various phenomena. I mean, when there is some interaction, what is the use of the interaction? Is it just a binding, or there is some physicochemical change of the particular substance? Okay. So, this is an interesting aspect of interaction. okay, especially in biochemical system, which is very important, in in biological system. So that can be nicely followed spectroscopically. So, in the next lecture, we are going to take up this particular aspect of this alteration of this prototropic equilibrium, and how that can be nicely followed fluorimetrically. So, this example we are going to present, and maybe a few more examples we will take in respect of this protein fluorescence. I mean protein fluorescence in the sense that protein systems we will take. In that case, either intrinsic protein fluorescence is used up, is employed, or maybe extrinsic fluorophores are used, and just protein has been used as a matrix, or maybe as something, as a system of your study. I mean just to have diagnosis, I mean just to know more about what is there within the protein stuff that makes such alteration or such gives such effects. Okay, so that can be followed nicely with respect with the help of fluorescence spectroscopy in conjunction with absorbance, maybe circular dichroism spectroscopy, and so on. So that we are going to take up in the next lecture. So till then, thank you.